made it to Friday, last day of classes. You guys want to guess what's in my thermos?
Beer.
It's coffee. I'm a professional. All right. Come on, get real. All right, and I need it too. Okay.
I know, isn't Irish coffee the best?
Oh yeah, wonderful. Yay, last day of class, but we still got to do some things. Okay. So, I said we were going to have a little competition with 11 o'clock when it comes to eval rate. And I said that there would be a prize for the section that had the best eval rate. So I just checked in. I'll actually show you the proof. So we're going to have 10 o'clock. We're going to have 11 o'clock. So when we go to 10 o'clock, you can see that the eval rate, a pretty solid 69.93. We also have to look at the 11 o'clock. And when we do so, what happened?
When did it end?
7% difference. I'm still actually pretty thrilled with the response rate in both sections, so thank you. Well, let's see. So you're at 69.93, and so there's two balloons. So you can see there's two options. There's first place, and then there's last place.
Why is that with the second place?
And for finishing in last place in the competition, I've got some matches. Now, so one of these balloons I designed to be better, and it wasn't the last place balloon. Oh, it's not. We have to put one first. So, that is my reward to you for finishing in last place. Woo! Yeah! Congratulations. I mean, there's two more over here.
That says second place.
I know, I didn't come up with the last place until I'd already written the second place one. And so I wanted to make sure that since you guys actually finished last place, you got the last place balloon. So, but in all reality, thank you for all of your evaluations, some of which I hope are good and I will see in a few weeks. So, let's see, we're gonna go until about 10:40 or so, and then we'll talk about some stuff. When's the exam? Tuesday. What time? 7 o'clock. And so I think we're gonna have 3 rooms. I think we're gonna have Andrews, Big Small, and Millington. Yeah, I know. I'll keep that in mind. I'll try to put Millington in the middle of the alphabet for you. So that's our 3 rooms. So that's that. The exam. All right, let's talk about the final because you're going to be excited at the end. And all right. So the final is going to be similar in terms to the midterms that we've seen. Very similar types of questions. It'll be about twice as long as a midterm. But you have how much time? You've got 3 hours. This thing is designed to be completed in about 2 hours, which gives you an extra hour to sit there and second guess yourself. So please take advantage of that hour by all means. So let's see. I was gonna say something else. Yeah, I don't know. I mean, it's gonna be relatively straightforward. Yeah.
So, will it just be the 3 hours that we have, or are you doing it Saha style, where it's like
I go to bed at 9:30 usually. So no, not usually that early. But point is, I'm going home at 10. So yeah, no one should need 3 hours, or at least more than 3 hours. And so we'll just say that no one can have more than 3 hours too. That's fair. Yeah, I've heard bad things about that sawhouse situation. Oh.
Will there be problems from the past exams on the quiz like there was last year?
I've thought about that. So I don't think there's going to be any exactly the same problems on this one, but I would expect some very similar problems, right? So sorts of things like how many stereoisomers for this compound, I'll just give you a different compound. So that sort of thing. But still, the previous exams should be really good preparation. And then when you're studying, I would focus a little more maybe on the second half of class, and the reason is just that a lot of the first half topics we have gone on and done a lot of different things with, right? And so some of the basic stuff like how many valence electrons are there, I assume you know that by now, and so it'll be lighter on first exam stuff and probably a bit heavier on second and third exam stuff. And keep in mind we haven't been tested on elimination or alkynes yet, and so that might be slightly more prominent than it would otherwise be. Yeah.
No calculator, right?
You
We can bring one.
you can bring a calculator, but I'm just gonna think you're cheating. I don't know why anyone would need a calculator other than to access bad things. So, yeah. Okay. So let's get rolling. Let's see how far we can get in this alkyne stuff. This will help me actually finish making the exam once I know what we've actually talked about.
Or we could just.
Or we could, no, that wouldn't be right, because then you could face an MCAT question or something that today was the key. You know, that's not good. So just a reminder, so in the notes before, I had someone ask me about this, and they said, Professor Walk, we had this secondary alkyl bromide in our notes before, and so we did an SN2 reaction when we were comparing SN2 versus SN1. But now we have a little bit more information, right? We didn't know about elimination processes at that point. So before, if we saw this, we'd say, well, that's SN2. That's all we know is SN2 or SN1, and we certainly have a strong nucleophile. But now we have some extra information, and so we have to keep in mind, go back into your notes, if you see something where it's a direct SN2, SN1 comparison, we now need to think about E2 and E1 type mechanisms that can take place. And so I think you have an example very similar to this in your notes. It should now be an E2 reaction, and so it'll be up to you to sort of update your thinking a little bit if we have some older examples where we didn't have as much information to apply at that point. All right, so we're going to try to do some alkyne business, and so just a reminder from the end of last class. Yeah, that. So we were doing some alkyne. So we learned that finally we are sort of like real organic chemists. And so we're real organic chemists because we can finally form some new carbon-carbon bonds, which is for the most part a lot of the point of organic chemistry, because organic molecules are mostly comprised of carbon-carbon bonds. And so what we're able to do is we're able to take a terminal alkyne, and we're able to take advantage of that pKa around 25. So that's fairly acidic for a CH bond. Many orders of magnitude more acidic than, say, methane or ethylene. And so once we deprotonate, we end up with an anion on that terminal carbon. And so it can act as a nucleophile, but specifically we're only going to be able to use it as a nucleophile with a primary alkyl halide. Why is that? So if it's a secondary alkyl halide, what is the question we ask ourselves? We ask if it's a strong base. Is this a strong base? Sure, it has a conjugate with a pKa higher than 25. So we're only going to be able to utilize this nucleophilicity with primary alkyl halides, but it's still really, really useful. And so you can see that if we add to a primary alkyl halide, we're able to form a new carbon-carbon bond. All right, so the longest cold in the world, by the way. So we're going to talk a little bit about alkyne preparation. So alkyne prep. So let's see, really, we're just going to talk about one type. So what you can do is you can prepare an alkyne actually from an alkene. So how do we do this? If you're given an alkene, so we'll show our alkene on our z-axis. So we'll have a couple of ethyl groups coming forward. what we can do is we can go ahead and we can treat this alkene with Br2. And so if we treat it with Br2, what kind of reaction is going to take place? So that's what would we call it? A halogenation that goes through an electrophilic addition, right? And so we're going to add a bromine to both sides of our alkene. And furthermore, all right, so we're doing a halogenation. How does this thing add? Is it going to be a syn addition or an anti-addition? It's anti, right? Because we go through a three-member transition state, we end up with a bromonium. Chatty, come on. All right, so what we'll end up with after bromination is a product that will look like this. All right, so we've done an anti-addition. We end up with our bromines. This is stuff that we've seen before. And then what we can do is we can add in some of this right here. So we saw this last time. Whenever you see something like NH2 minus, what is that almost always going to act as? It's going to be a strong base, right? That's the base that we use to deprotonate our alkyne. And so if we have a strong base in here and we treat this to this treat this compound with NH2, what kind of reaction is going to take place? Yeah, it's going to be an E2, and so furthermore, we're actually going to see two E2s. So what we'll do is we'll first, all right, so we'll say that we do two E2s, and so the first thing that we'll eliminate is these things can rotate, so we can take this hydrogen and this bromine, and so we can rotate such that they're aligned in an anti-coplanar fashion and undergo that elimination. And so if we do that, and we do that rotation, what we'd see is we ended up back with an alkene. That looks like this. And so here is our first E2. And you would think that that's the only E2 we could really do. But here's a case, kind of like a new reaction. So if we continue treating this with the NaNH2, what we're able to do is another E2 with an sp2 carbon leaving group bond. And so we've never been able to do an E2 reaction in an sp2 carbon, but in this case, we are able to make a very strong base. And so furthermore, would you say that the bromine here and the hydrogen here are sort of anti-coplanar to each other? Yeah, so you've got sort of your bromine over here going out in this direction, and you've got your hydrogen back here going in that direction. And so they are anti-coplanar, and because they're trans, they're able to undergo that sort of E2 mechanism. All right, so let's say that we have this thing and this thing, anti-coplanar, which will allow us to undergo an E2. And so then if we eliminate those two guys, what we end up with should be an alkyne that looks like that. So we have a new alkyne. Good for us. So we're given an alkene, we're able to brominate it, and then do a couple of E2s. And so by eliminating those two bromines, we're able to skip back to our alkyne that we're aiming for. Any question? Yeah, so what it is think about it this way. And I guess I sort of drew this a little backwards. So let's say that to keep in the way that we've oriented our molecule, let's say that we're eliminating those two, right? And so if we eliminate those two, we end up with a bromine and an ethyl here, and then a hydrogen and an ethyl here. And so that's what we see with our alkenes. Yeah, thanks for that. Okay, so that's the one way that we'll talk about forming an alkyne, is we can form it from an alkene. The next part, we're going to go to Roman numeral 3. We'll talk about, I was going to bring candy today, and I didn't. But at least I told you about it after the fact.
Don't bring any school up in the class.
Okay, I won't. I promise. Yeah, I might bring some candy to the final. That'll be nice. Okay, so let's think about alkyne reductions. Now we've seen alkene reductions, right? How did we reduce an alkene to an alkane? We should maybe do a little review on this stuff. And so to reduce an alkene to an alkane, you treat it with hydrogen gas and some sort of a metal catalyst, right? So like palladium on carbon or platinum. And so we can do the same thing with alkynes. So let's say we have this alkyne right here. So we're going to treat it with H2, and we'll treat it with some palladium on carbon. And so if you're noticing, a lot of the stuff that we're doing with alkynes is really similar to the stuff that we're doing with alkenes. It's just an extra pi bond, and so a lot of the transformations we find to be the same. And so what we would get is if we reduced this alkyne with H2 and palladium, we would end up with, let's see, ethyl, carbon, carbon, ethyl like this. And so eventually what we would do is we would reduce it twice, such that we ended up with an alkane. And so that would proceed through a sort of mechanism. Let's remind ourselves, is a hydrogen reduction, is it cis or trans? Yeah, it is cis, right? And so we would be going through an intermediate that looks like this. All right, so we go through our cis alkene because we have to go through a cis addition. But this thing, basically, once we've got this stirring with hydrogen gas, we know that this reaction is going to take place. So we're never going to stop here, and it's just going to end up doing it twice. All right, so that's not the most helpful thing in the world, but we should ask ourselves the question, can we stop at the alkene? Would you guys like to ask yourselves the question? A lot of momentum behind that. All right, can we stop at the alkene? The answer to this question is yes, we absolutely can. And that's going to be very, very useful because we're able to then open up some new plays into our playbook when we're trying to synthesize compounds. Okay, so our first opportunity for stopping at the alkene is going to be to use what is referred to as Lindlar's catalyst. All right, Lindlar's catalyst. So what is Lindlar's catalyst? You don't have to know specifically what it is. You can just know it as Lindlar's catalyst, and that's fine. What it is palladium that's on some calcium carbonate, and there's also some lead salts involved. And so it's this relatively highly specific catalyst, which you can just call Lindlar's catalyst. You don't need to know the specifics. And so the point of these lead salts is that it poisons the reduction such that alkenes are not further reduced. All right, so what that does is that gives us a strategy to essentially stop at that intermediate, which we were flowing through before with our hydrogen and our catalyst. All right, so of course, we're still going to need H2, and it still proceeds with syn addition. Yeah.
What do you mean poison? Like,
Yeah, and so that's the term that people use. Basically, it makes the alkene unreactive to the reduction, right? And so we say that it poisons it, because typically we would expect our hydrogen gas and our metal to just flow right through the alkene and go straight to the alkane. But instead, we now have what we call a poison catalyst, and so it'll do that reduction from the alkyne to that alkene, but then the alkene's no longer reactive. So the catalyst has been poisoned to that second transformation. So we're able to stop at the intermediate. And this is pretty useful. So for example, if we have a given alkyne as such, and we treat it with H2 and the Lindlar's catalyst, we're going to end up with our cis alkene only. So that's actually even more useful because we're not going to have to worry about stereochemistry. We just get one product, it'll be the cis alkene. I hear a lot of people coming in and out of class. Okay. I was just noticing. Alright, so we'll learn one other way to do these reductions, and so that'll be number 2. And so that'll be use sodium with ammonia. And so what that does is if we have a way to get the cis alkene, what do you think this gives? This gives the trans alkene. And so now we have a strategy to obtain either. So in that case, we will end up doing, I guess, what's kind of like an anti-addition. And we get trans. All right, so we get trans alkene only there, so good for us. All right, so that's reductions. We can reduce to the alkene. We can take either selectively the cis or the trans, and so that's two really useful tools. One note. All right, so what we're using is that sodium. It's just sodium metal. That's why it's not, these things aren't together. That's why we use a slash here. So that's literally just sodium metal in ammonia. And so what you want to make sure is that if you see an alkyne and you see sodium metal in ammonia, that is not the same thing as this, right? Because this will lead to the trans alkene. What will the blue one lead to? That will lead to the deprotonated alkyne, right? So here we've got a strong base. Here we've got a reducing agent. So just don't get those two things mixed up. If you see if you're using sodium metal, that's going to be a reduction, okay? So how much time we got? Boy, just blowing through this class. I didn't mean it, so don't. So reactions of alkynes, we'll do a few. And so we'll just say that these are going to be very similar. Some of you might need to come back and review the podcast. Very similar to alkene electrophilic additions. And so we'll see how far we get in this. So number 1, we're going to first talk about the addition of HX. And so we've done the addition of HX to an alkene. What kind of regioselectivity does it have? It has Markovnikov, and so that's not going to change. So we're basically doing the same sort of reaction. It's just now we've got 2 pi bonds from which we can react. How many people you think are in here that are not in my class? So, we're still going to follow the Markovnikov's rule. We're going to undergo Markovnikov addition. The first step's going to be what? Protonation. It was protonation of our alkene. Now it's going to be protonation of our alkyne. And so in undergoing this protonation, we have 2 possibilities. So let's see. We can protonate the carbon on the right which will lead to that carbocation, or we can protonate the carbon on the left. Which will lead to that. And so which is the more stable carbocation? Yeah, so this is a secondary carbocation. This is a primary carbocation. We're just going with the same rules. So nothing changes there. And so from there, what we'll end up doing is we'll have plus Br minus. And so what will occur? Let's see. It doesn't matter which side we're ultimately adding to because we're not going to have stereochemistry in the product. So this is a terminal double bond with no stereochemistry. So what we can end up with then is our ethyl group, a proton. All right, so we end up with that. But I will add that it can be very, very difficult to stop this reaction with the alkene because it's very hard to put precisely one equivalent of HBr in there. And so what you can, let's see, I missed something, didn't I? All right, so that's a bromine, sorry about that. All right, so once we get to the alkene, though, again, these are going to be hard reactions to stop. And so if we say that we have one equivalent of HBr, then what we're going to do is we're going to form this product right here. But sometimes what we're going to do is say that we have an excess of HBr. And so if we have an excess of HBr, that means that there's another molecule of HBr right here that can go on. And so are these two things reactive with each other? Yeah, absolutely. That'll just end up doing another electrophilic addition. And so now we undergo the same mechanism we know. Are we going to protonate the left side or the right side? Well, we'll protonate the right side because we've got a primary versus a secondary, and we want to form that secondary carbocation. Yeah?
How did you get the second one, so the ethyl carbon?
You're talking about this one?
Yeah.
Yeah, so what we can say is that this is the less stable carbocation, and so we're not worried about that one too much. So I was just showing that there's two carbocations that could form. We're going to go with selectivity where we have the more stable carbocation. So we're just following Markovnikov's rule.
And it doesn't matter whether you put the bromine on top or bottom.
It doesn't because there's no stereochemistry in the alkene, right? So
What if there were though? What if instead of CH2 on the other side, you had like another?
yeah, and I mean, and then presumably you could get multiple products, but I'm trying to keep it limited to like terminal alkynes where there's not going to be a lot of options. Yeah. All right, so then we're going to do another addition of HBr, and so eventually what we're going to find is we end up with a product where we've added bromine twice. We're not going to have a stereocenter, so we don't have to worry about stereochemistry. So we end up with an excess of HBr adding to our alkyne. Essentially, we're going to do that addition of HBr twice to go from the alkyne to the dibromoalkane right here. And so there's two possibilities. So if we add one equivalent, we'll stop at the alkene. If we add what we just call excess HBr, meaning there's more than two equivalents, more than the HBr we would ever need, then we'll go all the way to the end of the alkane. All right, so number 2, we will do. I feel like you guys want to blow up a balloon? Yeah. All right, so this is the balloon that you do not deserve. This is the first place balloon. This is the balloon that winners.
We're all winners at once.
So this is also a hydrogen balloon if you have sensitive ears.
Oh man, I'm excited.
Those are safe. Boo, 11 o'clock. All right. All right. So hydration. addition of H2O. And so we've seen this before. We've been able to hydrate an alkene. We've learned multiple ways to hydrate an alkene. So we can do that with water and catalytic acid, or you can do an oxymercuration, remember? And so that's another way that we can do a hydration. All right, so in this case, with an alkyne, so we'll say with alkynes, we can't use our catalytic acid. Isn't that sad? We can't use it. And so we can't use it because alkynes can undergo other pathways and do these polymerization processes, and so you're going to end up making plastic, not the stuff that you're trying to make. So it is kind of cool. I mean, so a lot of polymerizations are mainly organic chemistry. So we can't use the catalytic acid, but fortunately we do have our oxymercuration pathway, so we'll say instead we will use mercury acetate with H2O. And so we've seen that before. Everyone remembers exactly the oxymercuration mechanism, right? All right, so we'll walk through it again, except now we'll do it with an alkyne, because it gets a little different with an alkyne. It actually is pretty useful, because what we're going to find is we add one oxygen, but we don't end up with an alcohol. And so let's see why that is. So let's take our relatively simple alkyne. So what we're going to react with our alkyne is going to be our mercury acetate. So remember, mercury's got a lone pair. And so remembering that the oxymercuration goes through a three-member transition state, much like a halonium type mechanism, what we'll end up with is this three-membered alkene ring. As such. All right, so we get to that point, and so then we treat with water. I keep switching that to an ethyl group. That is a hydrogen. All right, so now we've got our water here. And so our water's got two options. It can add to the carbon on the left or the carbon on the right. Which carbon has more partial positive character? The left, right? It's just like carbocations. Think about which carbon would be the more stable carbocation. And so we know that the one on the left would be, so we've got more buildup of partial positive charge on the left. So what that means is that our water is going to end up adding to that left side. And so that will lead to so that leads to this structure. So we want to get to a neutral structure. So how do we get rid of our positively charged oxygen? Yeah, so we'll deprotonate with a base. So we're able to deprotonate there. So ultimately, we don't want the the mercury acetate in our organic molecule, as you might have expected. So what we're going to do is before, let's see, what did we do before? Before we did a reductive workup, I think, with sodium borohydride. We don't have to do that now. It's just going to be a water workup. And so we've already got our water in there. The mercury basically wants to fall apart. We don't worry about the mechanism, so don't worry about mechanism. Basically what it's going to lead to is this product right here. As such. Okay, so that is where we might expect to stop, knowing what we know now, but this is a special kind of molecule, and so notice that there is an alkene, and furthermore, coming off of that alkene is an alcohol. And so what we're going to refer to this kind of molecule as is an enol. Very, very creative. All right, so we're going to call this thing an enol. And so what we find out about enols is that they are not very stable. And so we're not going to worry about the mechanism of this next process, but basically what we're going to find is that there's going to be an equilibrium between our enol. And so it's going to be an equilibrium that highly favors this other product. And so basically we just obtain this other product on the left. What we end up with on the left is going to be a ketone. And so what we end up with is our ethene. Basically, our unit of unsaturation, or our hydrogen deficiency, that double bond gets moved to the oxygen. And so you end up with this compound right here. And so what this is referred to is keto enol tautomerism. And so the thing to remember here is that when we hydrate an alkyne, we're going to get briefly to that alcohol that we're used to getting to, but what's going to occur is this rapid equilibrium where we actually favor our ketone, and so hey, now we have a way to make ketones. So that's the first for us, I think. So, well, I guess we could do that with an oxidation of alkenes. I'm sorry, an ozonolysis of alkenes, but this is another way we can make a ketone. So, we're going to go keto enol tautomerism. And so just to define, I guess, that word, let's say when we talk about tautomers, we will say that they are constitutional isomers that are in rapid equilibrium with each other. And so basically there's special cases where we have constitutional isomers that are actually in equilibrium with each other, and so we're not going to worry about mechanistically how it works. There's actually different pathways that these things can tautomerize, but that's the definition of a tautomer. All right, 1038. Really briefly, I just want to get this other one down. And so we'll say that, is this number 3? So we can also do a hydroboration followed by an oxidation, and so we know what's going on here. What we want to add is that instead of BH3, we're going to use, I think this is sec-isoamyl borohydride, and so we just call this SiA2BH. Don't be worried about this. Just treat this like it is BH3. But we're going to find that it's necessary to use this whenever we do these hydroborations with an alkyne. And so what this compound looks like is this right here. And so the one thing you can say is that it is fairly bulky, right? And so we're going to use that. We're going to find that we need that steric bulk to basically do this hydroboration. So quickly, we'll look through an example. So let's see. This is going to be it. This is going to be our last example. Boo, we love you, Professor Wall. All right, so let's take this alkyne right here. And so we are going to treat it with this SiA2BH. And so again, we're just going to use the boron hydrogen bond to do our hydroboration. And so remember, we're going to have more partial positive there, more partial negative there. When we treat it with our compound, of course, we found that the hydride has a partial negative, the boron has a partial positive. And this is just like when we did the hydroboration with the alkene, so we're just matching up our partial charges. And so what's going to happen is these two things will react as such. And so we end up with this structure. And so the reason that we have to use that big, bulky borohydride is because if we were just using BH3, basically we could do this same process and end up with 2 borons sticking off of our carbon there. And so by using the big, bulky borohydride, we're able to prevent that second addition. And so we can just end up doing what we want to do. So once we're here, we just do our oxidative workup that we've seen before. So really, this is a fairly good reminder. of what maybe you should go back and look at. And so this compound right here, we have an alcohol next to an alkene. What do we call that? That is an enol. Is an enol stable? It is not. And so we're again going to undergo keto-enol tautomerism. In this case, we're actually not going to end up with a ketone. We're going to end up with this structure, which is what? Yep, and so this is an aldehyde. And so you can see that we can also form an aldehyde instead of a ketone. So 2 options. We're basically taking advantage of the anti-Markovnikov nature of hydroborations here to form the aldehyde. Okay, so we'll say, we're not leaving yet, but we'll say that our notes are but in reality, yay, because it's almost May and we can relax a little bit. Yeah. It's the sort of equilibrium where we're talking it's like 99% that, 1% that. And so when you isolate this thing, this is pretty much what you've got. Yeah. Okay, so I didn't recognize her. It is 10:42, so this has been an awesome semester. First off, organic chemistry is a hard class, and you guys have been working really hard and done really well. So give yourselves a round of applause for being really, really awesome this semester. It's been really fun on my end to actually be teaching my specialty back at my alma mater. Just like my Gen Chem class in the fall, I took this class in the spring of 2006 in this room, which was exactly a decade ago. So now I'm teaching the class, and that's really cool to me. Those of you that have had my Gen Chem class, and this is going to be difficult, but we're going to make it work, I like to take a class picture. And so with 115 or 120 people last semester, it was really crowded, and now we've got like 150. And so we're just going to have to do our best to crowd in down here as well as, or as good as possible. And then as soon as we get our picture, you're free to go. If you're not in my class, I guess you're welcome to be in the picture. Yeah, and you know the rules, tall people, short people, make it work. I'll hide my bagel.
Yeah, Stonewall, you go back there.
Yeah.
No, it's like tall people in the back. You're like, yeah. You go back there.
I mean, we might have to get creative because there are already a lot of people.
So we stand up.
Some of you are going to have to kneel and just kneel.
Start a second layer.
It's like make windows. In the back, we can just like kind of try to.
I don't know.
We've got like 25 more people to come in here, so we're we've made what you couldn't end up doing. You can always kneel in this next row up, right? So that could possibly work. If you're really brave, you can always.
What he needs to do is get someone with a panorama, a camera, like a new panorama.
You get far, like they're not looking at it.
Will you hold this? I'm gonna need help getting up here.
And also leave room for me.
Oh my god. Shift down.
He said to get on the table. Not to on the table? Yeah, sure. I don't want to block you out. You're a true spirit.
I'm waiting for my picture taker.
Think you had a better sight on there.
I mean, I was just trying to shift down so more people could probably see.
You were told, just go stand in the back.
It'll work.
Yeah, she's a cheater.
I gotta come somewhere.
Melanie's burger!
Just a little.
Alright, just taking a bunch of pictures. Everyone, alright, we're taking pictures now. Yay, Woo! Last day of class.
Raise your hand if you're not passing this class.
Raise your hand if you're not in this class. Just take a few more.
More.
Alright, just take one more. It's not mine. It's the department's.
Oh, shit.
Alright, yay!
And now we're stuck.
We survived.
I got one more class and one more chance to see the Sanderson.
Happy last day of class.
Yeah, so I'm next to the recorder. Freak the professor. Miller? Yeah.
It's in a folder outside of my office. Yeah.
You guys,
We were ready, and there were people outside, so I grabbed one.
I took the photo, Nick. I took the photo.
Yeah, so we gotta take it care of.
You didn't come to Inorganic. I was there.
why?
Because we played Jeopardy.
I'm gonna try to do something Monday. I should have some free time, so I don't know how to do it apparently, but
No, I don't want to.
Sorry, what?
yeah, so we'll just do the stuff we talked about. It gets a little more complicated without
And also, I don't think you can do it. So if it's itching, true that. Will one of the tests be someone?
Yeah, it's not gonna be.
There will be like something.
It'll probably be. Yeah.
3 hours probably gonna be enough. I guess. Appreciate talking to you. Do I want to come over?
You can email me whatever you prefer. We'll make work. Yeah, man. Absolutely. All right. Yeah. Good.
Please see you again. I'm not teaching any higher level classes.
Just Orgo 2 in the summer. Then I'm back to the general class.
You have to have a different professor.
Hey, my office isn't, well, it might be moving, but it should. You can always stop by. I'm always right
So
there.
actually, a little bit. Get that chess game.
Yes, definitely. Yeah, see ya. Okay, yeah. No, absolutely. Yeah, definitely.
Go ahead.
Not me, not yet.
So the answer is D. Yeah, but you still got 4 points because I gave some partial.
Wait, I mean, I thought it was C.
No, it's B, and it's B because you would end up with like either your two possibilities are radicals, are this radical here or radical here. So this one would be present and stabilized. So this one is going to be the more stable radical. So you know it's yeah, let's see. I'll be here probably until 4. I'll text you.
Yeah.
All right, I'll let you know.
I'll see you.
Yep, see ya.
Okay, quick
Hey,
question. For
yeah.
the halogenation that we did at the beginning with the bromine?
Yeah.
Was that a radical halogenation?
That's just an electrophilic addition. So just like when we added bromine to an alkene, it's the same thing except
Okay.
with an alkyne.
Didn't we do that like when you have the two bromines? Wasn't that a syn addition though?
So that was an anti-addition because you go through that three-membered bromonium intermediate, remember? And so then the other bromine has to add from the opposite side.
Okay, is that a reaction that we did before, or is this an elimination?
It's an electrophilic addition. So
Okay.
you go back to the alkene
Okay,
reaction chapter.
I'll just
It's
go
one of
back
the,
to
you know,
that
the list of like 9 things we did.
Okay.
It's on that list.
Okay, all right. And then will you still be answering emails over the weekend?
To the best of my ability.
Okay, all right. Thanks very much.
Yeah, you're welcome.
Thank you very much.
Yeah.